Okay, now we're going to talk about friction. It's a force that opposes motion. We're going to define and identify frictional forces. We're going to explain the factors that determine the amount of friction, determine the frictional force and coefficient of friction between two surfaces, and just have fun. Now, the key thing to understand is friction opposes motion. There has to be motion or an attempt at motion in order for there to be friction. Now, there's two different types. There's kinetic friction. Kinetic means moving, so we're talking about the friction in something that's already moving. And then we also have static friction, is the friction in something that isn't moving. It's the reason that when you first push something, it's harder to get it going than to keep it going. If you look at the difference here in the fact that molecularly what happens is, surfaces are not smooth, so therefore the object sits down into the other object. And in order to start something sliding, you've got to get to the top of all those bumps. And then, of course, the more bumps you have, the more kinetic friction you're going to have. But it always is harder to start something moving than to keep it moving. Now, the amount of friction force depends upon the nature of the two substances in contact. And that's the Greek letter mu, which that didn't. Mu looks like this. That didn't show up as mu. Mu looks like this. It looks like a U with an extra leg. And then it also depends upon the normal force of the object. When you're in a flat surface, the normal force is equal to the weight, if flat. Now, that's all we're going to deal with right now. Eventually, we'll add in things that aren't flat, but right now, that's good enough. Now, the coefficient of friction. We're going to actually cross all that out because that didn't copy over right. Friction is fun, though, is the way to remember it. The force of friction is equal to mu times the normal force. And the easiest way for me to remember that is that friction is fun. It's simply a ratio of the force of friction to the normal force. So if you rewrite it, you get mu is equal to the force of friction divided by the normal force. Now, we have a couple labs coming up on this, but I wanted to introduce it before we do the labs this time. And notice how the static friction is always greater than the kinetic friction. Just remember, friction is fun, and you'll remember the equation. Now, when you choose mu, you can look at a sled sliding down the hill, a desk at rest if you want to move, car tires rolling freely, car skidding across pavement. You have to look at both the surfaces in contact. So you would have to look at what the sled was made out of and snow or ice. You would have to look at what the desk was made out of and what surface it was sitting on. You would have to look at the rubber of the tires and also the surface it was going on. And then also the surface of the tires here and then pavement. So you have to consider both of them when you're working on it. So let's look at a sample problem. The brakes are applied, causing the rubber cars of the tire to slide on the surface. The tires encounter the greatest force of friction to stop the car on dry concrete, dry asphalt, wet concrete, and wet asphalt. Well, the greatest force of friction is going to be the greatest mu. And the greatest mu, and again, we're talking about something that's already moving. So therefore we're talking about kinetic as it slides. So therefore, we're going to look for the highest mu, and the highest mu is going to be that. So dry concrete is going to give you the greatest amount of friction. That's the reason you slow down when it's raining. Slow down if it's raining. Just remember that. Physics makes you. Now, to calculate the force of friction, we're simply going to use the force of friction depends upon the two surfaces in contact. Remember, that's a mu. It didn't copy over right when I went to the new slide. So the force of friction is equal to mu times the normal force. We're going to combine this with Newton's second law and free body diagrams to solve problems. So the diagram below shows a 4 kilogram object accelerated 10 meters per second squared on a rough flat surface. If the applied force is 50 newtons, what is the magnitude of the frictional force? Now, first of all, we want to draw a free body diagram. In our free body diagram, we have Fg going down, we have Fn going up, Those are the same length. I ran out of on the screen, and we have 50 newtons this way. And based on the way they're talking about it, I'm going to assume that the force of friction is less than that. Now, I'm going to choose this direction to be positive. You get to choose what positive is. We might as well use it in the direction that the object is already moving. So now I'm going to say the sum of the forces equal m times a. And since this is sitting on a surface, we're talking about the x direction. I don't need to worry about the y direction. Although the y direction does factor into it because it tells you that the normal force and the weight are equal to each other. So what I'm now going to say is, I'm going to start with my positive ones first. I'm going to say 50 newtons minus the force of friction is equal to m times a. Okay, now let's plug and chug the rest of the way. 50 newtons minus force of friction. Well, m is 4 kilograms. A is 10 meters per second squared. So I get, if I move f of f to the other side, well, no, let's leave f of f on this side. F of f is equal to 40 minus 50, and those are both newtons. So therefore, f of f is equal to 10 newtons. Now, notice how you come out with a positive 10 because the negatives cancel out. What that means is that you guessed correctly here in the fact that we pointed that in the opposite direction. If it had come out with a negative value, then we would have realized that we chose unwisely in the first case. So the force of friction is equal to 10 newtons in this case. Run it back through if you're not sure about it. Okay, now we have a horizontal force of 8 newtons is used to pull a 20 newton box moving right along a horizontal wood surface, and the mu is equal to 0.3, excuse me. So now, when we draw a free body diagram, we have Fg going down, Fn going up, same length. We have 8 going this way. Now you can call that the applied force if you want, or you could actually just leave it as 8 and friction's going back that way. I'm going to assume friction is less than that, but I don't really know. Now, F net is really nothing more than the sum of the forces. And again, we're talking about the x direction. So it's the sum of the forces in the x direction. So that, well, that didn't copy over right. So now I'm going to say simply that, again, I'm going to choose, it's moving to the right, so I'm going to say right is positive, just to remind myself. Now, so I'm going to have 8 newtons minus the force of friction is equal to m times a, and we'll get to that in just a second. But what I'm looking for now is what that value is. So this is going to be 8 newtons minus the force of friction is mu times Fn is my unknown. So I have 8 newtons minus mu is 0.3. There's no units on that. And the normal force is equal to the weight of the box, which is 20 newtons. So 8.3 times 20 is 6. So therefore 8 minus 6 is 2 newtons. So that's the first part. Okay, the other thing I'm going to want to get now is the acceleration of the object. If I want to get the acceleration of the object right here, I'm not 100% sure what that was, so we'll scratch that out. The acceleration of the object, well, sum of the f's is equal to m times a, so therefore a is equal to the sum of the f's over m. So the sum of the forces is the 2 newtons we had before, divided by the mass. Now here's where you have to take a little bit of a jump, or not a jump, but at least a refresher course. If the weight is 20 newtons, that means the mass is 2 kilograms. Remember, 2 kilograms times 10 meters per second squared would be 20 newtons. You can use 9.8 if you want, I don't care. So when you reduce that down, I get 1 meter per second squared. The math gods are happy. You've done both parts. Cool. Let's look at another one. Compared to the force needed to start sliding a crate across a rough level surface, the force needed to keep it moving. Well, remember, when you have a surface, the bottom of your object is rough. The top of this is rough. So what happens is they sit down together and they press into each other. So what happens is you have to get to the top of those bumps before it'll start sliding. So therefore, it always takes more to start an object moving. And if you think about that, if you've ever moved something, if you've pushed a couch across the room, you have to push harder to start the couch moving than to keep it moving. Same thing if your car runs out of gas. It takes 4 people to push the car to get it going. Once it gets going, one person can go jump in the driver's seat. Now, a car is moving at constant velocity on a level road. Compare the magnitude of all types of frictions to the force being put out by the engine. So let's go to our free body diagram. We have a car going down the road. Okay, there's my car. Artistic ability abounds in my family. FG goes down. FN goes up. Remember, FN only exists if you're in contact with something. Okay, now we have an engine force. We'll just call that FE. And also going backwards, I have the force of friction. The key thing here is constant velocity. As soon as you see that, you know the sum of the forces equals 0. So therefore, the engine force is equal to the frictional force. And that's the thing we will use in the next couple friction labs, which will help us understand it. Hope this helped.